Okay, I think that we're good to go. I'm sure that more people will join as we go. I will ask you now to mute yourself. And our speaker for today is Francis Albarede, and Yigal will present him. So Yigal, go ahead.
Okay. Hi, Francis. Hi, everybody.
Hi, Yigal.
Hi. We are very happy and honored to have Francis Albarede presenting his talk today. I will give you a very brief summary of his academic history and achievements, because if I make it the full thing, he will not have time to present his talk. So Francis got his PhD with Claude Allègre at the Institut de Physique du Globe in Paris in 1976, and then he went to Caltech to work on stable isotopes in granites, right?
Yep.
Was it you, Taylor, that you worked with?
Yeah.
Okay, and then from there he moved to Nancy. He stayed there until 91, and then from Nancy he moved to Lyon, where he is now. And throughout the years, Francis made major contributions to numerous fields of geochemistry. First of all, solid earth geochemistry, paleoenvironment that we'll hear today, medical geochemistry, and now in the last few years, he has been shaking the world of archaeometallurgy. And through this latest work, I became to know him more closely. Over the years, he also received numerous prizes. I will just mention two of them: the Goldschmidt Award and the Holmes Medal by the European Union of Geosciences. And he has been really a leader in the field of geochemistry, and a lot of people here and elsewhere know about his work. So Francis, we're very happy to hear you today.
Okay, thank you, Yigal, for these very flattering words, and that's very nice to be with. I would say in a place where I know so many people. By the way, I'm glad to meet Hagit. She never met you, Hagit, and it's nice to see you here. I know your work, and I think thank you for this very nice invitation. And I'm, as usual, I'm going to try to tell my story, a Sealand type story about the ocean, and try to explore what we can say about ancient ocean if we take a more chemical point of view, more than most people do in these days who are geologists and like this. So I'm going to start with the presentation here, with paying my respect to two strong characters of geochemistry who are not with us anymore, and I admire a lot, is Wally Broker on the left. And to tell you how much I used Wally's concept, this is the state of my book. You know, it's been a book he wrote with Peng in 1982, and on the right was another strong fellow, and amazingly creative. It was John Edmund, who passed away in 2001. Was a very difficult character, but an amazing scientist. So that's what I wanted to say as from the outset. So if I can, oh yeah, just have to click here. So let me set the stage first and tell you for, I don't want to insult anybody's intelligence. I know that I'm facing very fine scientists who know a lot of things about this topic. And three milestones in the evolution of the understanding of water chemistry. First was Silene. Silene in 1961, actually, the first paper, I think, was 1959, realizing that minerals may act as buffer for fluids surrounding them. Okay, here is the case of a reaction between kaolinite and potassium, which gives you some kind of mica. We don't care. This reaction here is not very important. Plus a proton, and this is what is in the Silene's paper, and it's at the beginning is say, well, the water is what they call the reversed weathering. Actually, there is a weathering at the surface of the Earth, and the reverse weathering here. And the way John Edmund phrased it, the reaction in a proton-rich, cation-poor environment, which is weathering, is reversed by interaction with a cation-rich, proton-poor solution, which is seawater. That was actually the foundation of. But that's not enough, because Wally Brocker pointed out that we cannot simply restrict the chemistry of the ocean to a simple equilibrium problem. We'll see that it's still, Silene's approach is still absolutely relevant, but not directly to the ocean. And Wally said, okay, we have to consider kinetics, and we championed the box models. Didn't invent them, but he championed them and told us that seawater chemistry depends on rate of supply of individual comment through the river, the rate of vertical mixing in the sea, like in the Southern Ocean, and the type of material formed by organisms, silica versus carbonates, for instance. Then came John Edmund. 1979. How old was he? He was 36, and he's the one who found with Jack Corliss and Diamond, I think, black smokers first on them. People have been looking for these black smokers for years and years, and these guys found it in the Galapagos. They're not black smokers. They were actually hydrothermal vents on the floor, on the seafloor. Black smokers were discovered in 1978, actually. And they realized John Edmund was actually had this wonderful paper that nobody knows in the Ewing's volumes. Black smokers consume the alkalinity added to the ocean by rivers and replenishes the protons consumed by weathering. This is extremely important. So in a sense, John Edmund made a synthesis between the two, the previous point of view, and that was actually wonderful. So you can see the ocean, the modern ocean, or whichever ocean, maybe an old one, as a chemical reactor with an inputs and outputs. Okay, the input is gain. Here is in blue, and first of the major input is runoff. Okay, but we have outputs, the loss of chemistry to sediments, and today it's essentially carbonates. But back 3 billion years ago, there was no carbonate. So whatever, most people think there was a little bit of carbonates, but nothing really that important. And we had the output was iron formation, banded iron formation, whatever you think. Then we have some little more complicated system, the high temperature hydrothermal system, which is mid-ocean ridges. The output is seawater. The ocean loses seawater to the hydrothermal system and gain hydrothermal fluids. Likewise, low temperature hydrothermal systems, the low temperature weathering, no, it's not weathering, it's alteration. output of seawater and input of our low temperature hydrothermal fluids. And you can write an equation. You can make some assumption about you can make some assumptions about steady state or not. You don't have to, but you have some fluxes here. So we can work with this equation and actually trying to predict, while using the concept of residence time near this, but if you assume steady state here, the steady state of the ocean, we can reproduce most of seawater chemistry today reasonably well, okay, with fluxes. So this is high temperature, this is low temperature, this is chemical output, this is riverine input, the runoff, and this is the composition of, and this is what goes to the. Yes, this is the calculated seawater. So you have a number of elements. It doesn't work well for rubidium and lithium for obvious reasons, probably absorption. But the system works reasonably well. It also works for isotopes, and I'm glad to advertise for this paper that hasn't been really well quoted, although we were the first to ever measure strontium isotopes in black smokers with my friend Jean-François Mister and Annie Michard and the whole group of people in 1981. And you can consider what the system is. The strontium enters through the runoff and is removed by limestone precipitation. And on the side, we have a system called mid-ocean ridge that receives seawater with a 7,6 strontium of 0.709 and actually reacts with basalt and gives something at 703 or 704. This is a system like this, and this is extremely important. So how does the system change through time? The runoff contribution to the ocean is something variable and depends essentially on the runoff, and the runoff itself is controlled by the proportion of Earth's surface above sea level. It looks obvious that we had some continents, but something important that actually was a suggestion by Nick Arndt, who pointed out that most volcanic eruption 3 billion years ago, or 4 billion, no, not 3 billion years ago, 2.5, actually took place under sea level. So the proportion of the Earth's surface above sea level will condition the amount of material removed from continents. And the second aspect is, which is known as Urey's reaction, is the pressure of carbon dioxide, which dissolves in meteoric water and actually reacts with the Earth's surface above sea level. Something which was right under our nose for years and years. I remember Claude Allègre and Keith O'Nions, Al Hoffman, Jan Weiser, and all these famous people who actually consider strontium isotopes in carbonates. And that's extremely important. You measure strontium carbonates. It's a bit like measuring lead in galena, okay? There is a very little rubidium-strontium ratio of carbonates is very low, so strontium isotopes are essentially frozen by limestone. So we know the 87-86 strontium ratio of seawater through limestones. And we have that kind of situation here in the yellow plot. Here, you can see it here. And you see that something is going on. In red is the Mantle contribution. Okay, it's relatively easy to figure it out. And we see that it's only by, let's say, 2.7, 2.4, that actually we start having a major difference between carbonates and the Mantle. And that's extremely important. And we were bickering about what it meant and about how much continent was formed. But we couldn't see something simple, actually shown by these guys in 2008, Flamand, Coltis, and I can't remember. When you get old, you don't remember the name. And Patrice Rey, that's right. And you see by the tell, so well, it just tell us how much continent was actually sitting above sea level, because when it's below sea level, there is not much going on in terms of weathering, and we have actually here a measure of the amount of continents above sea level. That's important. Another point with which I disagree with the part of the community working on Precambrian, on Archean and Precambrian material, is the meaning of phosphorus. Phosphorus is an extremely interesting element, first because it gets into each parts of life in DNA, in the ATP, ADP, system, in phospholipids and all the things. And this is the statistics of phosphorus through time in all kinds of sediments here. And the blue shade shows the +1 sigma distribution here. But it's clear, that phosphorus in sediment has been rising more or less continuously for over 3,000 million years, 3 billion years. That's interesting because the only source of phosphorus, the only input of phosphorus is river. There is no input from anywhere else. Basalt weathering, low temperature alterations, everything is a sink, not a source. So it means that, which is bad omen for water words. We need phosphorus fluxes, and phosphorus fluxes are associated with continents. No continents above sea level, no phosphorus, and it's bad. It's a bad thing, or continents or volcanoes, or you can have something like Iceland, of course. But we see that we have an increase in phosphorus, which is telling us that the amount of surface above sea level and that's been increasing. And if you try to fit this with through time, and you see that if there is today 30% surface above continental surface above sea level, today in at 2.4 giga-years, we only had a few percent, 7%. Of course, there is a big error bar, but you can say that at 3 billion years, there could not have been a lot of continents because there was no phosphorus in sediments. Okay, and there are some thousands and thousands of samples. It is very robust. So what does a water world look like? You can see, the modern ocean on the left. You have the modern ocean with the Gulf Stream, which is due to the vorticity balance, the standard model of the conveyor belt popularized by Wally Brocker. And here you have the Gulf Stream. Here you have the broad return flow. And what is today considered standard is the oceanic circulation. That's called, some people call thermohaline circulation, with water forming in the north here, following here down at the 3,500 meters, something like these, going over the mid-ocean ridges and the return flow, surface flow of warm water is right here. You realize that everything is controlled by plate tectonics, but the trends today is to consider that this conveyor belt is probably not correct, and it's not thermohaline circulation. Oceanic circulation is not a thermal machine. It is something that actually responds to forcing by winds and turbulence. This model is probably confuses causes and effect. If we had an aqua planet, we would have something looking like Jupiter, essentially, and with some circulation, some zonal circulation like this, and it would be very different, okay? And we have this kind of, with the Ekman pumping, we have this kind of mixing in the aqua planet, and that doesn't resemble what the standard conveyor belt popularized by Wally Broker. So let's talk now about inputs, outputs. We have a chemical sedimentation. Main components are calcium, magnesium carbonates, and it's essentially the flux of alkalinity coming from continents. We'll come back to the concept of alkalinity for the few of you who haven't heard about this extremely, totally central concept, which is the sum, essentially, of all the positive charges in the water. Iron formations, essentially banana formation. And that's what you could consider this at the time we didn't have a carbonate material. Well, actually, the alkalinity was taken up by iron formation, and to some extent absorption of clays. So a major conundrum is that something that some people deny. I know that John Grotzinger hates that plot, but it's there is something that it's difficult to go against. So Ronoff already in 1964 and Garrels and all these guys, they all came up with the same plots. Here's the H is the volume of the different sedimentary rocks here. And what you can see is that limestones are abundant today, but essentially did not exist 3 billion years ago. If they exist, like in South Africa, they were sitting on top of preformed recycled continental crust. It's not a standard deposit of the normal ocean in the Archean. So this is something I can read because I have my own thing here. In the modern day, 80% of the alkalinity is recycled in river. It means that limestone weathering produces alkalinity, but which is ancient alkalinity. 20% is juvenile alkalinity coming from the weathering of silicates. So this is an example of these 2.5 all Campbell and Campbell-Rand carbonates in Transvaal. But as I said, you know, this is this paper by Sumner and Grotzinger in 2004. But these carbonates are very special. They are on the shells of continents. This is something very unusual. And these carbonates are underlain by a felsic basement, and they were deposited on the continental shelf, but nothing like today on mid-ocean ridges and things like this. So remember that output should be decomposed, should be actually broken down into a high temperature output and of seawater, an input of hydrothermal fluids on mid-ocean ridges and maybe back-arc basins, and output plus input should be broken down also on ridge flanks, but at low temperature. You'll see why it's so important. Okay, the ridge flanks and mid-ocean ridges are very different. Here is something you all are familiar with. It's vaporization curve here in depth, here in meter. This is temperature here. And essentially, to tell you something that you never heard is that water boils at 100 degrees C. And when you, and then when you increase the when temperature is increased, the boiling point increases, okay? And what's going on here? Seawater boils at the temperature, higher temperature when pressure increases. The effect of depth depends on the planetary radius and therefore the gravity. And water thermal expansion and compressibility sharply increases near the critical points, which defines the temperature of eruption. When we reach 350, 400 degrees, we have thermal expansivity and also compressivity exploding, which is why, contrary to what you read in some places, the water never interacts with magmas, but water interacts with hot basaltic crust, at 300, 400 degrees, and then essentially it's a geyser. So it's important that the 350 degrees of black smoke is some kind of a magic. So let's now go around the different systems and see what we can say about the different controls. And the first one is essentially the proton balance of the ocean, something understood by Seelan and Edmond's group and a long time ago. And water rock interaction, when we have weathering or low temperature alteration, we take CO2 from the atmosphere, we make H2CO3, and we lose the protons to the crust. And we lose by exchanging the protons from the H2CO3 against calcium, sodium, potassium, you name it, okay? That's very important. The low temperature weathering and low temperature alteration are actually proton sinks. In contrast, high temperature thermal activity is a proton source. For instance, all the black smokers on the East Pacific Rise have a pH value between 3 and 4. Okay, I'm not going to talk now about photochemistry. I don't have time for this. But essentially, if you log the sodium over H plus here, you see this is temperature here. You see that here we don't have a lot of H plus. When we put albite into a solution and you heat it up to, let's say, 50 degrees or 100 degrees, we don't have much protons and so we remain at high pH values. In contrast, if we are at 300 or 350 degrees, reaction between albite and water gives you paragonite. We have this equilibrium, and here we have a lot of protons. So protons are consumed on the continents and they are actually produced on the mid-ocean ridges by all these reactions about the same. Okay, we have something a little more complicated as the effect of temperature. Here is the ratio, just like in the previous plot, but with other elements. It's sodium, potassium, calcium, magnesium, iron, aluminum, whatever, versus temperature. You have the same effect here. At the high temperature, water rock interaction produces a lot of protons here. And there is also an effect of chlorinity just by charge balance here. And for instance, you plot here the amount of metals with N plus charges, and you see that the slope for calcium, magnesium, and iron is much, it's larger than for sodium, potassium. So it means that the ratio of of calcium to, let's say, sodium, for instance, increases with the chlorinity, which is something very important that was used as a thermometer for geothermal systems. Second, that's the most difficult part. The most difficult part is electron balance. Modern atmosphere has a large proportion of oxygen. We know where it comes from. And nitrate and sulfate are the major electron acceptors in the ocean. Okay, we want to make a biological engine work, and we have some guys taking care of nitrate and sulfate and of your electrons, which are nitrate, sulfate, of course, and oxygen. But if we look at the Archean atmosphere, which is almost no oxygen, that's what most people think. My friend Hiroshi Omoto disagrees with this, but he's in the minority. Okay, so we have a problem finding electron acceptors, and people have been arguing forever. Our suggestion in the paper that I will mention to you is that actually the electron acceptor is a reduction of iron 2, there's a reduction of CO2 by iron 2, a reduction of CO2 to give a methane by iron 2. We'll see. Now let me show you how we get to this bold claim. So you all know about band and iron formation. They're quite spectacular. Okay, thick magnetite bands. Let's forget about the rest, the other minerals. Okay, and magnetite bands suggest a long iron 2 oceanic residence time, and they suggest that Archean and early Proterozoic seawater were rich in iron. We want to show something. You see why it is important to think about the residence time. And there was Fanny Thibon's PhD 2 or 3 years ago in Lyon, working on this. Okay, and I will go back to this. It's not properly organized. And what we do is estimating iron residence time from sediment cores. So this is our system, the usual system, input, output. We have hydrothermal sedimentary, we have a band and iron formation here, and we have an exponential response. We have the folding time, which is equivalent here to the residence time of iron. And we'll see, and we have a clock. It works, it's as good as anything else because we have, today we know that cobalt deposition rate is more or less constant within a factor of 30, 40%. And we extrapolate that back in time. And we use this as a chronometer. And we compare it wherever we could with the uranium-lead dates, and it works extremely well. But the advantage of a uranium-lead data is that cobalt, you can measure it everywhere, every millimeter if you want. So you can get some cobalt clock here at Hammersley and other places. It's consistent with any other evidence we can have and gives the band and iron formation sedimentation rate of, let's say, 1 to 10 meters per million years, which is equivalent to the sedimentation rate of modern deep sea sediments. That's quite interesting, actually. Okay, we use this clock here, and we have that kind of record here, the iron isotopes versus the relative age in million years, because the cobalt clock doesn't give us an absolute age, but a relative age. And we're getting something which is here the residence time. And we have several points where we can make that calculation. We have a very long residence time for iron, which is orders of magnitude longer than the residence time in modern in the modern ocean. So if I go back here, I can tell you quickly that we are using this to calculate the amount of iron, the concentration of iron in the ocean, which is a ferruginous ocean, clearly in the pre-great oxygenation event, which is much higher. Okay, it's 10,000 to 1 million times more concentrated than in the modern seawater. So modern seawater is limited because its iron is oxidized, okay, and precipitates as iron hydroxides, iron 3+ hydroxides. The problem is that if we look at the equilibrium between magnetite or ferrihydrite and an iron-rich ocean, and do a little bit of of chemistry, we find something bizarre. Here we have a CO2 plus Fe2 plus whatever, we don't care. Magnetite here gives magnetite, methane, and protons. Whether we do that with magnetite, some people say, oh, magnetite is not primary. Okay, well, yeah, let's make it with ferrihydride. Let's make it with a greenolite, which is an iron-rich serpentine. Okay, we have more or less the same equation. Okay, so essentially, the largest concentration of iron 2 reflects the CO2 iron 2 equilibrium, and essentially CO2-CH4 ratio is entirely determined by the amount of iron in the ocean. And what it's telling you is that the atmosphere was probably relatively rich in methanes, much more so than people expected. When I say much more, it was probably percent or tens of percent. Okay, we have this methane to CO2 ratio versus pH, and here is the amount of iron in seawater. And you see that if we are somewhere around here, around 7 here, we have the CH4 CO2 ratio, which is about 1, something like this, which is pretty high. And we get similar results with ferrihydride. So we have this ancient ocean containing iron 2 plus, which is the alkalinity of the ocean. Let's compare the ocean, the modern ocean, and an ancient ocean. Okay, the alkalinity is, I stole this from Wally's book. Okay, it was pretty good. And what is alkalinity? You have the charges here, the cations, and sodium, potassium, magnesium, and multiply by 2 because there are 2 plus here. And you compare it with chlorine, sulfates, and whatever. And whatever is here is not balanced entirely. It's called alkalinity, and is a little bit of borate, but you can actually ignore it. And then you have here the alkalinity, which is the measure of how much cations is actually taken to the ocean here. Well, what's the situation? What was the situation 3 billion years ago? We had sodium. We don't really understand sodium. Calcium, we didn't have much because, as I told you, there is no carbonates. There is no carbonates. Potassium, I don't know, it doesn't count, but we probably had a lot of iron too, and it had to be balanced by chlorine and HS minus, and we don't really know what's the alkalinity. But what we say, Archean iron 2 played the modern role of calcium 2 plus iron and carbonates to regulate ocean alkalinity and buffer the pH of the ocean. Let me skip this. So how can we explain the whole thing? And in O, with this wonderful paper by Terry Bowers and Hugh Taylor in 1985, they calculate the mineral composition, the mineral assemblage that could be in equilibrium with seawater. And here is the transformation coordinates. See, when you're 100% transformed on the transformation of the rock goes to completion, that's 100% is right here. But essentially in the oceanic crust, we're somewhere here. That's the volume percent of alteration phase. And what do we have here? In the water that has extensively reacted at 300 degrees with the oceanic crust, with amphibole, with this funky mineral paragonite, which probably has been dissolved a long time ago, albite. Here is epidote, and this is clinozoizites, that's another thing weird, and chloride. Essentially, we have the green schist facies. Okay, the green schist facies is equilibration of a basaltic composition with some hydrothermal rock, some hydrothermal solutions. That's something we can. So this is, let's do some Seelan type exercises here and try to control iron 2, calcium, iron 2 plus, calcium 2 plus, sodium plus, etc. At 100 degrees or 350 degrees against Terry Bowers and Hugh Taylor. And you can take these kind of equilibrium. You say, oh, yeah, I prefer another equilibrium. But in principle, if they are at equilibrium, it doesn't matter. So we have a buffer here of iron 2. We have a buffer iron 2. And we see that we have 25 iron 2 plus here. And we have here 50 H plus. We have a rate proportion of 1 to 2. Same for calcium, actinolite. Same for sodium, albite. It's probably not the reaction. This is probably zeolite more than anything that controls sodium, but this is a very difficult problem. And we can write this equation is iron 2 plus over H, and let me close it because I don't see it here. Iron 2 plus over the square of H plus is the constant depending on temperature. Same thing for same. So we can essentially calculate a number of things, defining alkalinity here, which is the sum of all the charges plus minus chlorine, which is pretty small numbers, 2 millimoles per kilo today. And we can actually remove all this H plus. So write an equation. Essentially, what we find is H plus is defined by chlorine at a given temperature. That's what it is. And we can use the thermodynamic data, and we have H plus as a function of chlorine, which is a real problem today. Okay, we can be smarter and consider also the complexation constant, but this is just technical here. We have iron, for instance, which is complex as chlorine, as double chlorine, and whatever. It doesn't matter. So chlorinity is becoming the problem. We know how to calculate. Well, let me go back here. What you can see here is a log of chlorinity. You can see here that the H plus increases with a given slope. Magnesium increases with the log of the chlorine. That's the Gilles-Michar's calculation here with a slope which is twice the slope of H plus. Potassium has the same slope, but we have a very good idea of what's going on in the ocean. Okay. So the chlorinity of the ocean is something very poorly defined, which is considered one of the major problems of geochemistry today. Okay, Bernard Marty tried to solve that by analyzing fluid inclusion in cherts. It doesn't really work because he measured argon isotopes, and argon isotopes, you know that in the atmosphere we are at 300 here, and actually he has inherited argon in this in this fluid inclusion, which shows which shows I have to go back. It doesn't do exactly what I want. Okay, it was here. Yes. It cannot be in equilibrium with an atmosphere because the ratio here is 1200 instead of 300. That's not the best way, but the idea is absolutely excellent to measure the chlorinity of the Archean Ocean. Now we bring it up together. We have a number of fluxes. Okay, we have the here the modern ocean, and here we have the ancient oceans with a number of things, and we see where the fluxes are. These are the fluxes. There is a transfer of alkalinity, transfer of protons, transfer of all these. Okay. The conclusion of this work is that I consider that the ocean has a low alkalinity for the simple reasons that we don't have much continents, and that CO2 is converted to a large extent to methane by iron 2. And second point is ocean chlorinity is the gatekeeper of ocean composition, and we don't know much about it. There are some things in the book by Holland, but I don't think very highly of this part of this book, and I can tell you why. It's clear that the fact that we have very little alkalinity going to the ocean explain the paucity of Archean carbonates, except on continental shelves, occasionally. And atmospheric oxygen is maintained at low level by CH4. And something happens during the great oxidation event, which we don't understand. My personal take it is that it's a genetic innovation of cyanobacteria because it's a very brutal event. The oxygenation is absolutely brutal, and I don't have time to talk about this now, but it's clear that something is going on here on a time scale of, let's say, less than 100 million years. And it goes, and this is incompatible with simply continents rising above sea level, because these processes are long processes. Okay. So I think we have to look for other explanation of for the great oxidation event. And well, there is a lot of things to understand. There is a lot of work to do, and this is, I think it's an interesting problem. And if you want to know more about what I told you, no, this one doesn't, well, this one doesn't want to move. You can go to our paper from last year with like, try to get this. I got so much trouble to get this paper published. Oh, wow. And people made a lot of comments I could not understand on chemistry, because too many geologists are not very good chemists, that's clear. So I will stop here and take some questions, and hope I didn't get you too bored by this problem. Thank you very much.
Thank you, Francis, for an awesome talk. Really, I really enjoyed it. And questions? Moti, you have one? I see you unmuted yourself. Go ahead.
Francis, first of all, a general comment. You know, our joint friend Steve once told me that alkalinity is the new ether. So everybody is talking about alkalinity, but nobody really understands it besides two people. One is Wally Brocker, and one is Boaz Lazar. But now it turned out that there is another guy that maybe understands what is alkalinity, and this is Francis Albarede. So that's my general comment.
Thank you. Don't forget that John Edmund was so fascinated by alkalinity that during his PhD, one of the major discovery by John Edmund is a way of measuring alkalinity by grand titration. There is a paper by John Edmund, 1970. He was 27, and this paper and this technique are still used today. This grand titration with something very.
So you say that there are 4 people that understand what is alkalinity. Okay.
Don't put me at the same level as John Edmund. Well, he understood that extremely.
There is Boaz Lazar as well. I don't know if he's listening to your talk now, but I think that he understands what is alkalinity. Anyway, my question is that, so you said that in the Archean time, iron was the guy, and now calcium is the guy. But now calcium and iron both are working. They are available. So what is now when you combine both of them together?
You can't combine them, because today.
Or are they competing? Or what's going on?
No. They're in the different galaxies. Okay, because iron today is iron 3, and it's totally insoluble. So there is no iron in the sea. Oh, there is a little bit, but nothing to write home about. Okay, iron is the trace elements but in in the old days, there was a lot of iron in the ocean, and there couldn't be too much sulfur because iron and sulfur, they like so much each other that they precipitate as a pyrite. So we have essentially, I didn't go into this because I wanted to keep the time limited, but prior to the GOE, most people consider that we had a ferruginous ocean, and between 2.4 after the GOE until probably the end of Proterozoic, we had a sulfidic ocean. That's Don Canfield's idea, which is excellent. And now we have sulfate. Sulfate is just waking up, and we see these beautiful changes in delta S34. They're so abrupt, okay, in the history. So we have these three periods. So that was the time of iron. There was a time for iron. Now there is a time for calcium. They never combine with each other. That's my feeling.
You know, one point more that is I think that you are well, we have something in common, which is the issues that the growth of continental crust, right?
Yeah.
So on the one hand, it appears that if you look on the general history of the Earth, then you see similar patterns of orogeny, right? So the orogeny, even if you go back to 3.5 billion years ago, and you go back to the early Proterozoic, the orogenic cycles are reacting somehow in general, right, in a similar way. But you are just, and this is, of course, an old notion. We know what you just told us, that in the ocean is behaving differently. So yeah, it came to my mind now, somehow. It came to my mind now when after your last sentences that somehow there is a kind of disparity between the orogenic cycles and the behavior of the ocean.
Of course, yeah, because what counts is how much of this crust is actually above sea level. Right. And it is that we were damn stupid in the 80s and the 90s that we were focusing on the amount of crust, which is a trivial question. I mean, I'm checking that Keith O'Nions and Claude Allègre are not around me, but this is so trivial. And we were all excited by this, but it was a red herring, okay? What is the most important, and I think we should credit Nick Harn for telling us, hey guys, everything is going on underwater.
That's true. This is the old good days of mines.
Yeah, no, it was after mines, sorry.
Okay, let's hear some more questions. Oded, see Oded waving. Yeah. Go
ahead. Hi, Francis.
Yeah, hi, Oded.
Thanks for the talk. In your talk, you treat the ocean by using basically water and mid-ocean ridges in a grand way. But my question is, what about subduction? And shouldn't we bring subduction into the calculations?
My answer is, you're probably done right. I didn't consider it. And how much water is actually expelled from the crust and actually transferred to the surface, to the atmosphere and the ocean. I think it's not an explored subject, and it is related to what people were doing in the 90s, or they call the subduction factory. The problem is we don't really know what's going on in terms of fluxes there, but you're perfectly correct.
Okay, and another question is about the mantle. You showed in one of the first few slides that the mantle contribution is more or less increasing constantly. based on the well, never mind.
Strontium isotopes.
This is fine for when you deal with ocean chemistry, but it's not a real Mantle contribution, because Mantle also contributes under the continents and into the lithosphere, and not only in mid-ocean regions. So it's okay to make the approximation that for calculating oceans, this is a Mantle contribution.
Yeah.
But one shouldn't make the mistake of calculating the Mantle based on this contribution.
What do you call calculating the Mantle contribution? Which contribution is not that clear to me?
Well, I think I relate to what you speak. I think with the you said that the phosphorus tells us, or no, the phosphorus measure the continents, but there was something else. There was a line.
No, there was.
You showed the strontium, I think.
Right. This was a diagram of the strontium isotopes.
Yeah.
But we know. Wait a minute. But we know very well what is the, or we think that we know very well what is the evolution of the strontium isotopes in the mantle. It's not related to the ocean. It's related to our knowledge of what is the strontium evolution of the mantle and what is the contribution of this strontium to the ocean. This diagram of the strontium isotope doesn't come only from the mantle, from the ocean.
Yeah.
This is the strontium isotope evolution of the mantle.
Okay. I made the mistake. If it's just a strontium, then no problem.
It's just a strontium. It's just a strontium.
Yeah, that's fine.
What is right? Yeah.
Okay.
Yeah.
Right. More questions?
I wanted to ask something.
Oh,
go ahead.
He's the expert on the alkalinity.
No, no, it has also two questions actually. One is with the alkalinity, that you still are left up with the problem, as you said, that you try to estimate it from a difference between two big numbers, and you want to estimate alkalinity, which you bound up to maybe a factor of even 10, maybe changes in alkalinity. It will still go into this difference, no?
Yeah.
That's one thing. The other one, you said that the chlorinity determines the chemistry of the ocean, and in that sense, how much you can change the chlorinity of the amount of chlorine in the oceans. It is maybe a few tenths of percent, not a few tenths percent, like 30%, 20%, I don't know, something like that. So it means that from what you say, it means that the chemistry of the ocean hasn't changed much, because you can't change the chlorine content of the oceans. If you take and dump up, as you showed, all those run of nice compilation, and you throw up all the evaporites into the ocean, and maybe the salinity will rise by something like 30%, something like that.
Yeah, you're correct on both counts. The first one, when I'm saying there is a less alkalinity, is not because I calculated it. I don't have the way of calculating it. I just have the way of two constraints. First, the amount of continents above the surface area of continents above sea level must be smaller than before. There are so many arguments. So input of alkalinity through the rivers and runoff alkalinity must have been, everything being equal, of course, must have been smaller. The effect of amount of continents above seawater is very clear. Second evidence is that whatever we think, whatever John Grossinger is trying to tell us, the amount of limestones in the Archean is small, and the limestone in the ocean that form of alkalinity is small. And I would say that band and iron formation alkalinity is probably rather small too, because there is a low deposition rate, but I didn't invent it, but it's clear that we don't have we don't have enough limestone, and the removal of alkalinity by limestone is very limited during the Archean, before the GOE. Does it answer your question?
Yeah.
Yeah.
And what about the chloride, the chlorinity?
And the chloride. The chloride, I don't have the faintest clue. And I'm surprised that people. So Dick Holland makes made some calculation by estimating the amount of evaporite. Essentially, I would consider the problem of chlorinity of the ocean in a relatively simple way. I can go with Jean-Guy Schilling calculating the amount of chlorine actually emitted by mid-ocean ridges when was it, in the 90s, or is the two wonderful papers by Jean-Guy. And we may have probably a constant flux of chlorine from the mantle. But then we have something which is totally non-linear. Is the amount of evaporite stored on continents. It's probably very difficult to make evaporite in the past. That's why everybody is using barite and barium sulfate to evaluate sulfur isotopes and strontium isotopes, and not anhydride or anything like this. There is none, okay? Because making evaporites at the bottom of the ocean is kind of not very easy. And then once you have some material rising above sea level, then you can change the flux of chloride by weathering, essentially. And then, but this problem is not well constrained at all. And that's why the Holland's calculations they're not quite relevant.
Francis?
Yep.
I wanted to make a comment following what Boaz just said about the significance or the importance of chloride in the ocean. And back in the 90s, Jim Morgan and I published a paper where we showed that basically a large number of elements in the ocean, we can predict their concentrations in ocean water based on the one hand, the tendency to form dissolved complexes with chloride, and then on the other hand, their tendency to be absorbed on surfaces of oxides and removed into the sediment. And therefore, this interplay between the dissolved and the absorbed tendencies basically can mimic their actual concentrations in deep ocean water, away from biological activities. So I think that this is something that, if we can have a better estimate for the concentration of chloride versus other anions in the ocean, will affect the whole suite of elements in the ocean, including trace metals and major elements. I can send you the paper. I think it was, you might be interested in.
Yeah, I understand what you're saying, and I would have the same reaction. What the most important, okay, it's something that this group of people working with Planaski and Reinhardt and all these guys, essentially, once you consider the residence time of an element in seawater, what comes around goes around. What you find at the bottom of the ocean is what you removed from continents, plus what comes from the mantle through hydrothermal systems. So if you consider some absorbed material, I'm right in the middle with this for zinc. The question is, what is going to be the residence time of adsorbed material in sediments? if the time between, because it's not going to remain adsorbed forever, because it's heated up, there's some diagenetic process. And so you can think of a box called adsorbed material, but the residence time in this box will be short. It's interesting in terms of processes, but essentially you have something which is coming from the ocean. This is a bulk flux coming from the ocean into sediments on a time scale in excess of the residence time of the ocean, of the element in the ocean. That's what counts. But essentially, that we cannot ignore the fact that what we find at the bottom of the ocean is exactly what it was yesterday on continents, okay, and on mid-ocean ridges. Plus or minus 1 million years. Who cares about 1 million years? Okay, that's the way I see it.
Yoni's been waiting very patiently and raising his hand. So go ahead.
Who is raising his hand?
Yoni, right? You have a question?
I'm more of a puzzling of something. I wasn't sure if so why not to assume that chloride concentration increases through time? If you only have a source from the mantle, right, and it's a conserved element, right, you should be increasing it with time. So if you think of the Wally's plot with the alkalinity, right, for the modern and from today, both the sodium and the chloride that you plotted are similar in concentration as they are today. But why would that have to be the case, right? I mean, if you're increasing chloride through time, then your whole charge balance of the ocean would be totally different, right? And then you don't have any constraints on your iron, and then you don't have any constraints on your methane for CO2.
On anything, yes, that's correct. The balance. I mean, the answer to your question is essentially how much chlorine gets stuck in evaporites compared to the increment of chlorine actually produced by volcanic activity, because we cannot assume that there was no chloride initially. I know that today residence time, chlorine residence time is something like 100 million years, something like this, but I don't know about what the situation in the past. And so if we store more chlorine in evaporites minus what is getting eroded, and whether it's higher or lower than the increments of that's a question. But I try to attract people's attention to some problems, not to constrain things that cannot be constrained with the available evidence.
I also wanted to say that it was a fantastic talk. I haven't ever seen such a systematic way of explaining the chemistry of the ocean before in such a short period of time. It was superb.
That's very nice of you. I really do appreciate that compliment. I really do. Some people hate it, but it's okay.
Okay, I think that we're well over time. And I'd like to thank you very much for this crash course in ocean chemistry through Earth's history.
Thank you all. I mean, I'm glad to have seen all these famous, these familiar faces that some of them I haven't seen in a long while. And I hope I can come back to Israel as soon as I can. And I make sure this time, Ecole, that will come and visit you and spend some time with you. Okay? Thank you so much. Thank you so much, and I wish you a good day if it's not too late. And I hope I got you not too bored by what I told you. Okay. Bye, everybody.
Bye. Thank you so much.
Thank you. Bye-bye.
Bye.
Hi, Francis.